Hello students, we are back into the discussions in this video. Right, remember what we're discussing so far is about the intersecting chords. We have so far discussed something about the chords which are intersecting inside the circle, like this. Coordinate B, talk of AB, intersecting with XY, intersecting at point H. This time around should be able to give the relationship that exists between amongst the parts of the chords as much as the two chords are intersecting inside the circle. So we saw that the relationship that exists between this chord AB and XY, as much as they're going to intersect, we saw that the part that's the AH is going to be multiplied by part HB. This is the same as XH, this distance from there up to here, multiplied by distance from here up to that. That's the HY. This comes in by similarity. A chords intersecting inside the circle. Today is a different story. We'd like to discuss now and again observe what follows when chords intersect outside the circle. Right, so here we talk of the external. That's the intersection. Right. Suppose we've got a situation here. Look at this. Here's the circle, and what I have a chord AB, like this one, another chord you can have what DH. Right. The two chords can be produced or extended to any other point outside the circle. Like say AB can be extended outside to a point somewhere, which can be a point that can cross with another chord like DH at somewhere maybe point what? Point T. Right, so here we'll be interested to see the relationship that is there between a chord AD extended to T and chord DH extended to T. So here simply like we have got two chords intersecting at one point outside the circle, that is external intersection at point what? T as such. What the relationship that exists. So to find that the relationship that exists between the two chords marked that they're going to intersect outside the circle, we also go by the same theory that we used that time in order to note what follows when the two chords are intersecting inside the circle. Issues about similarity. Right, so here in my chart, I'm going to draw a circle and have the situation well observed. Suppose we've got a circle like this one here. Look at this circle here. And I've got a chord that starts maybe from this point and goes outside like this. And another chord starts from here and goes outside like that. And the two chords are meeting here at point maybe T, where they're going to intersect. When you can produce this one out like that, they're going to intersect there. This chord is just D, V. This chord is M, N. Intersecting at T. Right, so this is what we have today. Right, now, what is it that we need to know about that? Definitely, you'll be able to appreciate that the matter I am extending these chords to outside, you find that these chords are already split into two parts each. We have got chord D, T split into DV and VT, and chord MT split into MN and NT. So here it means we're just going to look at the relationship that exists amongst the parts DV, VT, MN, and NT as such. Let's see, by similarity, it means I have to introduce triangles in there, which has to be proved that if they're similar, then we have to take the corresponding ratios and work out on it and see the results. So here what I'll do, I'll join point D to N like this, to form triangle DNT, and I'll join M to V like this. Look at this, to form triangle what? MVT. So let me just have this one. It's a different color. You can see that this is just a construction, and I'm going to have got this color here. It's just a construction. So if we're going to light this one formally, yeah, I know how you're going to light it based on the first discussions, other videos where we are to prove the light given whatsoever, talk over to prove things like that. Right. So here, what I'm interested in is just to see what is there about DVVT in relation to MN and what NT. So now, let's just begin by proving if triangle DNT and MVT if they are similar. So that out of which we need to obtain the ratios of the corresponding sides. Right. So by similarity, this is what we do. Look at this. It means we have got here in triangle. We talk of first the triangle DNT, DNT, and the triangle what? MVT. MVT. Those are triangles of interest. They carry the parts of those chords. Take a look at this one. How do you prove that the two triangles are similar? The most important test that you can use to test that the two triangles are similar is the equiangular test. That tells us if the three are corresponding, or say three pairs of corresponding angles are equal, then the triangles are similar. That's a talk of the angle equiangular test. So here we are. Let's now first of all get into the first triangle here. You'll find that in triangle DNT, and in triangle MVT, we have got this angle. Look at this one. I define this one as x1. That angle is the same as x2 here, meaning to say angle at M is the same as angle at D. Listen, you can look at this arc here. This arc here, VN, is subtending this angle at M, and this arc, the same arc, subtending angle at D. So by the first property we discussed about the angle properties of a circle, we'll be able to deduce that the two angles must be equal, angles subtended by the same arc. So I'll write here to say x1 is equal to x2. Right. Why? Angles subtended by same what? Arc. Like that. So it means the first A has been satisfied. Let's go to the second A. As such, you'll be able to appreciate that if you look at the two triangles, DNT and MVT, they both have a common angle, which is this one here. Look at this angle here. This angle here is common. So it means both triangles have got the same value at the second angle. So I'll just write here to say angle at T is common to both triangles. Therefore, it means again, if I'm using this equiangular test, it means the second A has also been satisfied. We have a pair here of equal angles. Now, what about the last one? The last one, it means we have to consider issues about the said angles of that triangle. But if you can look at the design of the diagram here, you'd find that the said angles in the two triangles we need to concentrate upon are angle MVT in case of this triangle here, this angle here, and in the other triangle, we have to talk of triangle DNT, where we have got this angle here, like that one. Now, we have no any notation about those angles, so that maybe out of which we can deduce that the angles are equal as we have done for the others. Right. But now, using mathematical understanding, that's the application, we know that in a triangle we have got three angles, and the sum of which is equal to 180. Now, what do you expect if two angles on one triangle are equal to the two angles of the other triangle, or say two pairs of what equal angles? We have them in the two triangles. What do you expect about the third angles? And it's just to be obvious that say the moment two angles like here, this one is equal to this one, and this angle is common here, we expect the remaining angles must also be equal. So which means in this case, we also have to deduce that say y1 is equal to y2 in that triangle. Right. So why do we say that? You write y1 is equal to y2. These are 30 angles of a triangle, and they must be equal. Right. So this, it means we have satisfied the three A's there. So what do we say then? We like that say, therefore, triangle DNT is what? Similar to triangle what? That is MVT. That's it. Listen, you write in the bracket, let's talk, say angle. That is equiangular test. Right. So now what is this about it? Once the triangles are similar, we expect that say corresponding angles of those two triangles must be equal. And again what? The ratios of the what? Corresponding sides of those triangles must also be equal. So here, let us now first of all obtain the ratios of the corresponding sides of the the two triangles which are proved to be what? Similar. So how do we obtain the ratios of the corresponding sides? So this is what we do. The moment you are proving that the two triangles are similar, like DNT and also triangle MVT are similar, it means the way you are writing the letters, it means the order of which represents equal angles. If we are there going to relate letter by letter, a letter alone can define an angle. So like here, it means that if I talk of a D, it means angle D can be the same as angle what? Angle M. And this one has to be observed here that is true. Right. The same N must also be what? V. Right. That's the way it should be here. So it means angle at N should be the same as angle at what? At V. So similarly, if we're going to use two letters in describing a quantity, here it means a line. That's just like a side. So here I'll talk of side DN. Now, in terms of ratio, the one we know about the word similarity, that the ratios of corresponding sides are equal. It means in this triangle here and this triangle, we have the ratios like DN 2. You remember that by the previous video, you can follow the link down here. While I introduced the ratios, the design can write it like say DN 2 what? MV. Write like this one. Must be equal to NT, middle, last, like that, to VT. Write VT like that. And this must be the same as what? DT. You see that? DT. To what? M, first, last. That is M what? MT. Just as we did in the first property above the what? Chords intersecting each other. So now if this one is true, but that the triangles are similar, then out of the three ratios which are equal to each other, we can be able to obtain two ratios which needs also to be equal. As far as this is equal to this is equal to that, they don't expect any two ratios again to be equal if we are going to be interested in them. So here our target is just like to see the relationship areas I explained. What is it about what we need to know about MT and MT and DT? Much that the two chords which are starting from DV extended to T and MN extended to T are intersecting at T. So what I'll do here, I'll obtain two ratios out of the three. We have got 1, 2, 3 there. That has at least within them the sides which are part and parcel of the chords we are discussing here. So I'll talk of chord D, V extended to T and chord M, N extended to T. So if you can look at the two ratios, you find that one of the ratio of our interest, it will be ratio which is this one here. I'll talk of this one here. So I just need to take only two ratios there, so that I have to observe what I need to see here. Right. So if I talk of DN to MV, I'll be talking of the parts like here. Talk of the D. Let's say talk of the DN. Not necessarily this one. This one not. This one not. This one not help us anything. You see DN and MV. Look at this. DN and MV. These are just lines which are just part and parcel of the construction. We want ratios which are pure, a target of our interest. Remember, our design was just like this. So we have to consider DVT and MNT. So just like which ratios here are carrying those parts here, just like we have got 4. DV, VT, MN, and NT. That are of our interest here. How do they relate if the ratio, if the chords are intersecting outside? So it means here, what we do, we'll skip this one out and just consider this one and this one. Right, NT, you talk of here, you talk of the, that's the NT, you talk of NT here, parts of this chord, and also VT, you'll be talking of this part of that chord again. Right, so, which means if we're going to exclude this one out, we'll remain with this ratio and that ratio. So what do we expect from there? It's the same, that is to say, the two ratios, that's NT to VT must also be equal to what? DT to what? MT. Why are the two equal? Because area, the three are already equal. It means any two pairs must be what? Equal to each other. The same thing. Let us now try to cross multiply the sides of those ratios. This by this and this by that. So it means I'll multiply this by this to have NT, that's now like therefore you're concluding NT, right, this now by cross multiplication, this by this, this by that. So it means I'll multiply this by this, I have multiplied by MT, that then that. This, it means, must be equal to what? DT, which is this one here, multiplied by what? VT. This by that. That's what we're going to have there. So now if I look at this type of analyzation, the conclusion from the ratios of the similar triangles, you'll be able to see that if we are to draw this figure again, omitting these parts which are constructed, it means we're going to have something that is just now like pure, having something like this, to say that every time I have got what a chord like DV intersecting with another one at T, like here I've got M, that's a N, that's why we have to take it. These were just part of the construction. You'll be able to appreciate that what we have produced here, it is just like we talk of DT times VT. Look at this one. It will be the whole of this distance here, D to T, multiplied by VT, must be equal to what? NT multiplied by what? MT. So here you look at the MT, longer distance multiplied by what? NT. Right. So this is always true. Somebody draws a circle and the chords, the moment the chords are intersecting outside. Please, students, be able to know that, say, when you take the product of the entire distance from, like, say, D to T multiplied by V to T, not from here up to that, should be the same as from here up to that multiplied from here up to that. That's the conclusion of it. Right, so that's it that I wanted you to get to know about it. So in the summary, briefly, just to make a conclusion about the intersecting chords, as the students be able to appreciate that this was just like an added part of the theorem, which is very, 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 very important as far as issues about the MSc exam is concerned. So in conclusion, let's talk of issue about the internal and also external. That's the intersection. Internal, we have got a circle like this. I draw a chord, another chord intersecting here at maybe T. This is H, X, M, D, and here we talk of the external. I have got a circle like that. Then this one have got chord C intersecting outside by meeting at V. Like say this is M, H, but this one is Z, Q. What we should expect is this distance from here up to that. Light multiplied by from here up that is the same as from here up that multiplied by T to D. When this is the situation we should expect to have HV multiplied by MV should be equal to what? ZV multiplied by QV. Light. So students, by this I will call it off in the video. The next video will be there as the last part of our discussion in the topic, where we just have to look at 2 examples that we can be able to appreciate the knowledge which can be applied based on the internal intersection and also the external intersection of the chords in the circle. Thank you very much for being together in the video. Thank you again.